Good morning, class. Thank you for joining me learning about radiography. Today's lesson is on X-ray tube structure and function. We will take a look at what an X-ray tube looks like and what makes it work. In the late 1800s, William Röntgen discovered X-rays while working with a Crookes tube, a cathode ray tube that was the predecessor of modern X-ray tubes. In 1913, General Electric Company introduced the Coolidge tube, a hot cathode tube that was the prototype for modern X-ray tubes. Essential requirements for X-ray production include a vacuum, a source of electrons, a target, and a high potential difference between the electron source and the target. A Pyrex glass envelope forms the basic structure of the X-ray tube and houses the anode and the cathode. The frame is made of strong, heat-resistant glass and contains a filament, which consists of a small coil of tungsten wire and a tungsten target. The air is removed from the glass envelope to form a near-perfect vacuum so that gas molecules will not interfere with the X-ray production process. The tube is fitted on both ends with connections for the electric supply. The two ends of the X-ray tube are connected in the transformer circuit so that the filament end is negative and the target end is positive during exposure. The source of electrons is a filament at one end of the tube made of tungsten wire. Tungsten is a metal element, a large atom with 74 electrons in orbit around its nucleus. An electric current flows through the filament to heat it. An advantage of using tungsten is that it has a high melting point, which enables it to last through thousands of exposures. Now let's talk about how X-rays are created. The tungsten filament is heated, causing electrons in the tungsten atom's orbits to spin faster, moving farther from the nucleus. Electrons in outer orbits are flung out of the atom, forming an electron cloud, or space charge. The electron cloud provides the electron source for X-ray production. Upon striking the target, the kinetic energy or movement of the electrons is converted to X-rays and heat. 99% of the energy is made up of heat and the last 1% are usable X-rays. X-rays are produced at the target due to either a sudden deceleration or absorption of the electron stream. These interactions of electrons with tungsten atoms may occur in one of two ways. Bremsstrahlung radiation is created when an incoming electron is suddenly slowed down, changes direction, and leaves the tungsten atom. The kinetic energy of the electron is converted into an X-ray photon. Bremsstrahlung is a German for breaking or slowing. The short term Brems is often used instead of the long word. Every X-ray exposure will contain photons produced from Brems interactions in the anode. To recap, Bremsstrahlung radiation is created when an incoming electron is suddenly slowed down, changes direction, and leaves the tungsten atom. Characteristic radiation is created when an incoming electron interacts with the K-shell electron and knocks it out of orbit. When the electron void is filled with an outer shell electron, an X-ray photon is created. Below 70 kVp, 100% of the photons in the X-ray beam are from Bremsstrahlung interactions. Above 70 kVp, about 85% of the beam is Bremsstrahlung. The majority of all X-ray tubes are produced by Brems radiation. In producing X-ray images, there is no difference between Bremsstrahlung and characteristic photons. They are produced by different interactions of the incoming electrons in the anode. Technically, this cannot be controlled. The primary X-ray beam is made up of both Bremsstrahlung and characteristic radiation. The wavelength and energy of the X-ray beam is said to be heterogeneous. This means that it is made up of many different wavelengths and energies. Although having at least one filament for X-ray production is essential, modern multipurpose X-ray tubes are dual-focus tubes. They contain two filaments, one large and one small. Only one filament is used at a time. Each filament is situated in a hollow area called a focusing cup in the cathode. The focusing cup has a slight negative charge. The shape of the focusing cup and its negative electric charge force the electrons to be repelled in the direction of an exact area on the anode target called the focal spot. The small filament and focal spot provide much better spatial resolution. Spatial resolution is the new digital term used to describe the sharpness of the structures recorded in the image. The small focal spot should be used for most body parts on small or average size patients. The large filament provides more electrons and strikes a larger target area. The large focal spot is used on larger patients or thick, dense body parts. The large focal spot can better absorb the heat generated by the increased exposure technique required for these patients. Modern tubes for general radiography have a rotating anode. The rotating anode is in the form of a solid disc with a beveled edge target. This disc spins during the exposure, so the heat is distributed all around the circumference of the disc. An induction motor is used to rotate the anode. Because this motor is sealed inside the X-ray tube, it works through electromagnetic induction, similar to a transformer. The term actual focal spot refers to the area on the target surface that is struck by the electron stream. The effective focal spot refers to the vertical projection of the actual focal spot onto the patient and image receptor. The line focus principle explains the relationship between the actual focal spot on the anode surface and the effective focal spot size. The actual focal spot refers to the area on the target surface that is struck by the electron stream. The effective focal spot refers to the vertical projection of the actual focal spot onto the patient and the image receptor. Here are 3 key points regarding the line focus principle. The size of the effective focal spot determines image resolution. The target angle determines the relative size of the effective focal spot. The steeper the target angle, the more significant the difference between the actual and the effective focal spot sizes. Although a small effective focal spot is desirable for greater resolution, a large actual focal spot is desirable to dissipate the heat of large exposures. The best solution would seem to be to use the smallest possible target angle. Before we end our lesson, let's talk about the anode heel effect. When X-rays are produced, not all make it to the IR. There is an uneven distribution of radiation intensity that is referred to as the anode heel effect. X-rays are formed within the target material and some are absorbed by the target as they try to exit. This creates a higher X-ray intensity on the cathode side of the X-ray beam. The anode side will have a less intense beam than the cathode side. It is important to keep in mind the anode heel effect when using the whole X-ray beam and the full length of body. Here are a few points to think about. There is greater radiation intensity toward the cathode end of the radiation field. It is significant when using the whole beam, such as using a 14 by 17 inch IR at 40 inches or a full spine at 72 inches. Examples include when imaging the full spine or entire leg. To mitigate this unevenness, place the patient's thinner portion of body part toward the anode end. If the anode heel effect is not used correctly, the result will be that the thinner portions of the anatomy appear too dark on the IR and the thicker portions will be too light. Thank you for joining me today. Please feel free and rewatch this lesson to go over the details of X-ray production and its effects. Make sure you use the bonus notes and flashcards by clicking the link in the notes section. See you on the next lesson.